Hello, Maxime. How are you doing?
Good. How are you?
Very well, thank you. Feel free to take over the screen. This is a great
Yes.
talk. I've heard secondhand. It was a larger version of it was given at the Postgres Developers Conference in Vancouver in the spring. I was not there, but my daughter was there, and she said it was one of her favorites. So I'm really looking forward to it. Maxime, I'll hand it over to you.
Okay. Thank you. Yes, indeed. So let me start by giving some context on who I am, what I'm doing, and why I'm here, what I'm presenting here today. Um, so I'm a PhD student working in Brussels, mainly on mobility databases. And specifically, I'm working on MobilityDB, which is a spatiotemporal extension on top of Postgres and PostGIS, and mainly adds new temporal and spatiotemporal data types to the database. And the main type of interest is a temporal geometry type, temporal geometry geom point, which can be used to represent the movement of or the trajectory of cars, boats, planes, and so on. And so this database is complete with these new data types, as well as indices, some operations, functions, and optimizations. And we realized that the indices that are being used, so these are GIST and SPGIST indices, just like PostGIS uses, they are not extremely efficient for temporal geometry points, simply due to their shape, that these trajectories are very long and have large bounding boxes. And we realized that the indices that use these bounding boxes are not as efficient as we would like them to. So I started this work for multi-entry indices with this purpose in mind. But then afterwards, we realized that it can be used for many other data types as well. And so indeed, when I gave the talk in PGConf, I was talking about data types that are native in Postgres, like multi-ranges. And so today I want to talk about some data types in PostGIS, so that could be that could make use of these new indices to speed up some operations, and hopefully this will be interesting to some PostGIS users. So as a first small example, let's start with multi-point types. So in PostGIS, one of the geometry types is a multi-point, which is simply a collection of points. And here you see an example with two multi-points, the blue pluses and the red x's. And so let's say I want to find all of my tuples, my multi-points, that contain a point that is within 2 units of the origin, in this case. Clearly on the image, you can see that the blue pluses is the answer, and the red tuple is not part of the answer, right? And so this is a query that typically would make use of an index, because we are searching for the tuples that have a certain condition. In this case, does my multi-point intersect with this region? Or actually, in this case, you could even use the distance within function for PostGIS. But the way the indices work in PostGIS and MobilityDB as well is that they store a bounding box of the geometry that they are indexing. And so in the case of collections of geometries, so geometry collections like multi-points, multi-polygons, it is a single bounding box that will cover all of these geometries. So in this case, you see the blue and the red boxes. These are the bounding boxes that will be inserted into the GIST index. And so when applying the same operation as before, the index will expect or think that both tuples might be part of the result, whereas only one of the two is part of the result. So we see that the index in this case creates too many false positives. And these false positives, they slow down the query because they have to be rechecked with the actual function, like d within in this case, and this will slow down the query. So this is a small example on points just to understand it easily. But this happens also in the real world, some real world use cases. And so this example was mentioned to me after the talk in PGConf by one attendee. So assume we are storing data of countries as multi-polygons. So in this case, you see the red polygon, multi-polygon, corresponds to the country of Russia. And since this multi-polygon crosses the boundary of longitude 180 degrees, you have a part of it on the right and a part of it on the left. And so when computing the bounding box of this multi-polygon, we get this very large bounding box, which covers the whole extent of longitudes. And this is not ideal, of course, because then if we want to check, we have a query where we want to find all of the, for example, the name of the country that contains a specific point. If that point is somewhere in Europe, let's say, we will check with the country of, or with the geometry of Russia, which we want to avoid because it's a large polygon and this slows down the query. And so we want to produce multiple bounding boxes. This is the idea. We want to split the tuple into multiple bounding boxes and index these bounding boxes in the index separately. And this is not the only example there is. For example, the USA has the same problem because they have some islands on the far right that are very hard to see, but which produce the exact same problem as what Russia has. And then there are similar problems, even though, for example, here France, even though it doesn't cross the longitude boundary of 180 degrees, still has a large extent because there are some islands that are spread around the world. So bounding box is also very large. So this multi-point example and here the multi-polygon are two examples that could make use of the index, where we want to split the tuple that we index into smaller objects, in this case still bounding boxes, before indexing them, with the hopes of speeding up the query because we return less false positives. Another example, which was the use case that we started with, are for trajectories. And this is equivalent to the PostGIS type of line strings, where you have a long trajectory or line string that covers a large extent. But since the trajectory is very thin, it might be that the overlaps returns false in a lot of cases. But storing the whole trajectory as a single bounding box in the index, you still expect, or the index still expects this trajectory to potentially pass through some, for example, a query region here in blue. And so we would like to split this trajectory or line string into a set of smaller bounding boxes before indexing. And this is slightly different to the previous case where we had the multi-polygon and we create one box per element, per polygon. Here we only have one element, one geometry, which is a line string, but we want to split this into smaller boxes. And so this is not completely new. In PGConf, there was already a presentation about something like this, an index, which has a similar idea. But the main use case that they presented there was for nested structures like HTOR, JSONB. But the idea is very similar. And so what we do is we add two new access methods, which are essentially equivalent to GIST and SPGIST, except that they add an extra step before insertion where they split the data tuples into multiple index entries before inserting them with the hopes of being more efficient afterwards, even if the index is a bit larger. And so in this case, these access methods are called MGIST and MSPGIST. The M stands for multi-entry and can be created in the same way as GIST and SPGIST index in SQL. So how does this work? And I'll go through this very quickly. The idea of GIST, this is a small schema where you see a multi-point for the insertion at the top right. You have a multi-point that contains 2 points. Typically what GIST does is it first calls a compress function, which will create this bounding box around the 2 points. So you see here the X-min and the Y-min, and then X-max and Y-max. So this is your bounding box. And then this bounding box gets inserted in the index together with tuple ID, which is a pointer to the tuple. And then during querying, the PostGIS support functions will add a query or an index predicate. In this case, if our SQL function is d within, the query predicate will be, does my multipoint overlaps the result of st expand? And then this query gets passed through the index and returns a set of tuples, which we then need to recheck with the actual database function. in this case, D within. So the difference between gist and MSPGist, MGist, is that before compressing, we call a function, a new function, a new user method, which is called extract value, which will split our tuple, in this case our multipoint, into multiple bounding boxes. It doesn't have to be bounding boxes, it could be also just multiple points or multiple polygons, because the compress function will be called afterwards still. But in this case, you see, we return two bounding boxes, one for each point, instead of a single one. And then we apply the exact same query. So the querying part is the same, or the query, the predicate is the same. But of course, there is a slight difference since now that we have multiple bounding boxes for the same tuple, the query predicate might match all of them or multiple of them. And so we might return duplicate tuple IDs. So we still need to deduplicate, but this is handled internally by MGist. And then after the deduplication, still recall the actual function, of course. So let's quickly see how this works in practice and the speed up that we can gain with this. So here I'm back to the example that I showed at the very start, where I have a set of multipoints in a table, and I have 3 copies of this table, one without index, one with a gist index, and one with mgist index. And then running the same query on these 3 tables to see the query plan and the speed of these queries. So the query that I'm running here is simply count all of the multipoints that have a point or are the distance within that multipoint and the origin, so make point 0, 0, is within 2 units, right? And you see here, this is the query run on the table without index, so we get a sequential scan. And mainly you can see that the filter, which is the D within condition, filters out most of the rows. So we start out with 100,000 rows. The query only returns 106 of them. And this takes about 47 milliseconds. But since the query removes most of the rows with the filter, we would expect this to be sped up with the use of an index. But then when we run the same query on the table that contains the gist index, we see that it's not really the case. So here we have the index scan and the index condition. And we also see amount of rows returned by the filters, which is very high. So it's still smaller than the sequential scan. So the index has a bit of use, filters out some of the tuples, but clearly not enough, because the execution time doesn't go down, and we still filter out 60,000 tuples. So the index in this case returns way too many false positives. And this is the example that I was showing before, because the bounding box of these multipoints cover the origin, even though the elements inside are not close to it. And so now running the exact same query now a third time, but on the table that contains a multi-entry gist, mgist index, we see that the index condition is the same, and the filter is the same, but the index itself returns much less rows, thanks to the fact that we split each multipoint into multiple bounding boxes, one per point, instead of a single bounding box. And so we see we only return 133 rows, with 27 of them being false positives. And these false positives comes from the fact that the ST expand creates a square bounding box. So the query value is a square bounding box around the circle that we're actually looking for. And we see also that since we have much less rows to actually filter out afterwards, the query speeds up quite a bit here, in this case, about 300 times. So this was the example with the multipoints. Let me show the same thing that covers the second example that I was talking about before. So with the countries and the multipolygons. So let's say I have here a table with countries. They have 2 important columns, the name column and the geometry, which is stored as a multipolygon. And in this case, we have about 260 countries in total. And then we can create either a gist or an mgist index on this second column. So let me run the query here. The query that I'm testing is simply, what is the name, select the name of the country that intersects, whose geometry intersects a specific point. And this point is somewhere actually nearby, near Brussels, inside Belgium. So this query should return Belgium, single value. And what we see here is that the index is being used. So in this case, the table had a gist index. So the index is being used, but the index returns 6 values, 5 of them being false positives. And if we investigate a bit, can find that these 5 false positives are France, Netherlands, but also Russia, USA, and Norway. So France, Netherlands makes some sense because these are near Belgium, but Russia, USA, and Norway appear because of the issue that I was showing at the start, where we have much larger bounding box that we actually want. So now if you run the same query using mgist, you can see that we end up with only 2 false positives, which are France and Netherlands, and we remove the 3 other ones. And since these other false positives contain geometries that were quite large, this was slowing down the query. So in this case, again, we have a speed up about 13 times. So now these were 2 examples for PostGIS data types, multi-points, multi-polygons. Let me quickly go back to our use case, which was for trajectories, the temporal geometry points. So trajectories, they are equivalent to line strings. They are very long, but very thin as well. And due to the fact that they span a large spatial and temporal extent, they can also create large bounding boxes and produce similar problems as we have in the other 2 examples. So the way they are stored in MobilityDB is the following. Typically, the data arrives as sequences or a set of tuples where we have some ID of the trip. In this case, MMSI corresponds to a vessel ID with a timestamp and then a position, latitude, longitude, which we can create a PostGIS point from. And then all of the tuples that correspond to the same trajectory are aggregated inside a single tuple. And this is how MobilityDB represents trajectories. This is very similar to how PostGIS represents line strings, for example. So this could be seen as a line string M, where the M represents the time dimension. And so these tuples contain long sets, long sequences of point and timestamp pairs. And we have the same issue as what I was talking before, is that since these line strings are very long, the bounding boxes are large, and there's a lot of dead space that the index doesn't know about. And so we want to split them. In this case, we have multiple ways of splitting. We could split 1 bounding box per segment. But since in our case of trajectories, we have up to thousands, if not 10,000 segments per trajectory, this is not realistic. We do not want to create thousands or 10,000 boxes per objects. So in this case, we just split into a smaller amount of boxes. So in the example, we have, I believe, 7 boxes. And this will already significantly speed up the index without making it too large. And so as an example, again, we have here a query where we want to find the vehicle ID and the trip ID of the trips that passed within 10 meters of some query points from a table of points, which just contains a few points, query points around the city. And you see the query plan again, using the bitmap index at the bottom. In blue, you see bitmap index scan. And you see that the index returns about 1,000 rows, although the actual results only contains 18 of them. So again, we have a lot of false positives. And since these false positives are a long trajectory, applying the filter afterwards, so the recheck, is costly. And so we get an execution time of about 31 seconds. And if we run the same query, but with the trips split into smaller bounding boxes, so using the mgist index, well, the index returns less false positives. So index returns about 60 tuples. 18 of them are correct, so only 41 false positives. And this speeds up the query by about 10 times. So in this case, I showed 3 examples, 2 from Postgres, 1 from MobilityDB, but there is an equivalent example that could be made with Postgres line strings. All of this is using code that is available. So we implemented this as Postgres extensions so that everyone could try them out if they want to. So these are 3 extensions, actually, 3 separate ones. The first extension, just called MEST, contains the access methods for mgist and mspgist, and is purely Postgres extension, doesn't have any other dependencies. And then the operator classes for the PostGIS geometry types are implemented in PostGIS MEST. And in this case, there is one operator class which does this splitting of geometry collections into a set of boxes, 1 per element. And the last example with trajectories is implemented in MobilityDB MEST. So feel free to look at this code or try it out if you're interested for your geometry types. So yeah, I'm getting to the end. Thank you for your attention. I'll answer any questions that you may have.
Well, thank you very much, Maxime. That's an incredible presentation, an incredible body of work.
Thank you.
One of the things which jumps out to me is like how many keys is reasonable to chop up an object into. Like at the limit, you can say 1, or you can say, like you said, 1 for every segment. Where's your code happiest?
Well, this depends on the use case that you have. For the case of trajectories, we found that the more you split, initially splitting creates a lot of speed up, but then the more you split, the less the speed up keeps increasing. And so about for these trajectories, the data set that I was showing, about 10 boxes is sufficient to get to the optimum. But it really depends on the use case that you have. And for example, I'm expecting that storing, let's say, rows as line strings might have longer segments. And so we could go one box per segment, right? But it's just in case of trajectories, this was not the case. So it depends. And also it's a bit of a trade-off between the speed of the query and size of the index. Yeah.
What's the dial that you turn to change that?
Excuse me? Can you repeat?
How do you change the splitting behavior in the index?
Yes, so in the PostGIS extension, each element in the collection gets 1 box. So there is at the moment no way of changing this,
right.
But we're thinking of adding that. And in MobilityDB, there is a parameter that can be specified. When we write create index, we can add a parameter which says the maximum amount of boxes that can be used per trajectory, for example. Yeah.
Right. Are there any version issues in terms of this? What versions are supported by the extension?
Yes, so the mgist and the spgist code is heavily based on the gist and spgist code in Postgres. And so we try to keep it up to date. Currently, the version is up to date with Postgres 17. So it will unfortunately only work with Postgres 17, but it's up to date at least.
Right.
Yes.
Any limitations on PostGIS versions? I'm guessing probably not.
In this case, not. So it's implemented by copying, of course, since it's very hard to work with the PostGIS types. We copied the lib-lwgeom library inside the PostGIS MEST extension. So unless the PostGIS version changes a lot and the code are not compatible anymore, it might have issues, but otherwise this is not really a problem.
Was there any appetite at the development conference to bring your work into Postgres proper?
Yes, there were some questions about that, about what the future plan was for this. And currently, I'm not sure yet. It's indeed a possibility because these changes are not that significant actually between gist and mgist. So it could be added to core of Postgres, but I still have to work on that and discuss with them to see if they're interested. Yeah.
Would that be as a new access method, or just as generalizing just to handle multi-key?
I think the easiest way would be to have these extract value methods as optional. And so if it's implemented, it would be a multi-entry index. If it's
Right.
not, it would not be. It would be a regular gist index.
Yeah. That sounds wonderful. So what are you doing next now that you've revolutionized spatial and temporal spatial indexing?
I'm not sure yet. So I'm getting to the end of the PhD, so I don't know yet what the future holds. Yeah.
Okay. Well, thank you so much, Maxime. It's been great.
Thank you. Thank you very much for having me.